All right, good afternoon, everyone. First of all, I'd like to thank Stephanie and Lucrezia and Tobias for inviting me. It's always a pleasure to be here. So as you can see, my title is not quite what Roberto said, because I decided to switch a little bit the topic so it's more appropriate for this session. So I will be talking about quantum mechanical restraints, and I will actually touch a little bit on validation later on. So as we all know, ligands need restraints. I hope that works. So because in macromolecular crystallography, the experimental data alone are not sufficient to define a small molecule structure. So here's an example. Here we have an electron density map. Oops. And I try to get the laser pointer here so everybody can see it. So here is an electron density map. We have a ligand. Fits.
Can you go back to the presentation?
Oh, that is interesting. I must have swapped here something. So let me try and figure out.
There's a button on the top.
Top left, yeah, I don't have this here. Okay, here we go. All right, I will not touch this anymore. So we need restraints. Here is an electron density map. And if we just wanted to determine the position of all these atoms of this ligand based on that electron density, that would usually not work. So what we typically are doing is we use restraints to guide refinement toward a chemically plausible model for that ligand. And so restraints supply a priori information. And so here's an example for restraint bond lengths. So here's a very small molecule, ethylene, and here are two atoms, the two carbon atoms, and we know that they are a certain distance apart. So the coordinates of these two atoms, they are independent. So one carbon doesn't really know of the other one in our refinement. But if we introduce restraints, this will keep the distance within a certain target value. So here 1.34 angstrom. And in addition, there will be a penalty if the distance deviates too much. So in other words, these restraints, they modify the refinement target function by creating relationships between independent parameters. So for ligands, what do we typically restrain? So
questions for Dorothy? Come on, take your seats, please. Need to make up time. Need to make up what we lost. Okay, so let's start where we left off. We need restraints. Off you go.
okay. All right, everybody woken up. So what is restraint? So I mentioned bond lengths, but we also look at valence angles, torsions, planes, and chiral volumes. So where do these restraints come from? So known ligands can be found in libraries. So they ship with the refinement programs typically. So in Phenix, for example, this is in the GeoStandard. This comes with the Phenix installation and nothing needs to be done. However, if you have novel ligands, there are several options. So typical approaches to get restraints for novel ligands is to get ideal values from, for example, empirical databases. So databases of small molecule crystal structures, such as the crystallography open database or the Cambridge structural database. Another way is to do some quantum mechanical calculations or a combination of both. So for novel ligand restraints, there are a couple of challenges. So first of all, many ligands are flexible. So if we just generate a single conformer restraint, this may penalize if we have some torsional, different torsions that are possible. Now, if we get our novel ligand restraints from QM-based methods, then this may be, this represents only the isolated molecule because this minimization is typically done in solution. If we use these crystallography small molecule databases, then there may be not exactly the same fragments in that database that we are getting our restraints from. So they may be similar, but not identical. And if we have truly new functional groups, there may be not in these databases at all, or there may be just a few instances, and they may be difficult to treat with standard QM methods. And in both cases, they ignore the specific interactions of the ligand in the protein binding pocket. So here's one example. I think, where's Roberto? He will recognize this figure. So in a study that he did, they took a hypothetical molecule shown here in the upper left, and then they used different restraint generators such as ASDRAG, GRADE, ELBO, and so on. And then they compared the final coordinates. So here is an overlay of all these generated molecules from these restraint generator programs, and they overlaid these final coordinates on this double ring portion of that molecule. And you can see here that this portion of the molecule varies a lot because there's a wide variation in torsion angles. So a priori, that's not really a big problem because once this will be fed into refinement, the conformational space can be sampled by the refinement program, or if you open this in CRUD, let's say, and do some refinement, real space refinement. But if you have poor or low resolution data, then it may be challenging to sample into that correct space. And so once you have your restraints file and you did refinement, what happens if there are large deviations from ideal? So here's an example. I look at a berberine molecule in a 2.34 angstrom resolution structure. Berberine is used as a natural dye. It's used in traditional medicine or as a dietary supplement. So it's of pharmaceutical interest. In this particular structure, there are 4 chains and each has a berberine molecule, and I'm focusing just on chain D. So let's take a moment and look at this molecule. So here is a figure of this. And so clearly there's not such a torsional variability as in the previous example, but still there are some things that are noteworthy. So here these terminal carbon atoms can rotate around this carbon-oxygen bonds. And so while there are here some rings, and these are typically very rigid, we have here 2 rings that can have puckers. So let's look at the density. It's actually the image I showed you in the first slide. The density looks okay. Yeah, there's nothing that really looks problematic. So we took this structure, used our restraints that come in with a GeoStandard library, and refined. So what turns out is that the mean RMSD for the angles is 2.4 degrees, and for the torsions is 48. So that's quite substantial. And here is a list of the worst offenders. So here we have the angles, the torsions, the ideal value, and here is the deviation from ideal. So we have a couple of angles at around -7, -6 degree deviation, and a couple of torsions. The worst one is 76 degrees. So the majority of these angles and torsions are actually in this central ring here. Now, what can we learn from the fact that we have here large deviations? And unfortunately, there's no clear-cut answer. It depends. And there are several scenarios that are possible, right? So number one could be that the ligand is strained, that genuinely in that binding pocket, the ligand takes on a conformation that has higher energy, and probably that is then used by the protein to do its chemistry. That could be one option. Then simply the ligand could be disordered, or even could be completely wrong. It's not there. So there's no experimental data that keeps this ligand in place. We've seen that this is not the case for this particular molecule, though. And then finally, are the restraints inadequate? Yeah, did the restraints program do something wrong, or do we just have incorrect conformers here? So to address this, we came up with this QMR approach. And the idea here is to do QM minimization of the ligand geometry in the binding pocket. So this approach will account for the influence of the local energy minima of the ligand, and it will take into account the in situ environment. And so once we minimize the ligand geometry, we will use that geometry as a target value for restraints. So I will guide you here through this berberine example. So step one is we focus on a ligand in the protein. Here it's the berberine, shown here in the violet color. And then we will identify a local environment, a cluster. So I guess that's a bit similar to the previous speaker, what has been done. So let's now focus on this cluster. And so we are taking into account by default all entities that are within 3.5 angstrom of the ligand. This takes into account also crystal symmetry. We are using entire entities. So if only one atom of a residue is within 3.5 angstrom, we take the whole residue. And then we also add hydrogens to make the charge of these residues neutral, because this is important for the QM minimization. So then we do the minimization. So focus a little on this berberine here, how it changes. So now I go to the minimized structure that is here. So I go here a bit back and forth. The residues are by default not allowed to move, but the hydrogens in the environment can move. But these are all things that can be changed. So to minimize, we use the program MOPAC, and we use a method that includes dispersion and hydrogen bond corrections, because these are interactions that frequently occur in proteins. And then once we got this minimized geometry, we forget about the residues. We just focus on the ligand. So here it's a little bit bigger, and we use the coordinates from this ligand as targets for restraints. Now, maybe you're wondering, where are we taking then the ESD values? So the deviations, we derive them from the original restraints file that we used. So let's compare maybe the two geometries that we have in our restraints library and from this approach. So in geostandard molecule is shown here in gold color, and in teal we have QMR. So, and I overlaid them here on these two left rings here. And what we can see is that here these carbons that have a rotational degree of freedom, here the angle seems to change a little bit, but the most prominent feature that is different is this pucker. And as a consequence of this change in pucker, this whole two-ring system over here will flip a little bit down. Okay, so what happens if we now use this kind of restraints for refinement? So here's the same table as we had before. The mean angle RMSD decreases now from about 2 to 0.8. And for the torsions, it decreases from 48 to 7. So this is a significant average increase. And if we look at the worst offenders, so again, it's the same as in the previous table, and we're looking here at the values shown in red, we can see that each of these deviations, individual deviations, decrease. So in summary, for this berberine molecule, we observe now less deviations from ideal. So there's a systematic improvement. Now the question, does it actually affect significantly also the refined model? So actually in the model, you will not see a lot of difference. So here is a superposition of the refined structures using either the geostandard restraints or the QMR restraints using the same color code, yellow and teal. And so they are superposed very much, so there's not much difference after refinement. Here is a little close-up, only showing no density and only no structures, and you can see that we have in that teal model from the QMR restraints, we have more pucker-like arrangement, which is expected. But there's also no real space in real space correlation coefficient. So you could wonder, is this maybe just a cosmetic change now, right? We use a different set of restraints. Model looks basically the same, but we have now a clearer idea of what happened, of the significance of these deviations. So this is just one example. Of course, we have to test if this works on many things. So we did some benchmarks. So we analyzed about 1,700 ligands. Of course, in the PDB, there are many, many more protein ligand structures, but we wanted to focus on specific systems. So first of all, we wanted to focus on well-defined environments. So we wanted to avoid any scenarios where there are other ligands, metals, or alternative conformations, because these may complicate all these quantum mechanical calculations. Also, it's important that there are no missing atoms. And as we all know, protein data bank, unfortunately, some structures have residues with missing atoms. Also, we focused on a certain size. We didn't want to take something that is too small or too big. And we wanted something where we can be sure that there is actually a ligand. So we focused only on diffraction data that have resolutions better than 3 angstrom and have sufficiently good real space correlation coefficient. Also, an important thing is to look at charge. If the charge looked suspicious, that's often a sign for incorrect protonation. And we were not so interested in common crystallization solution components, but more on drug-like molecules. And last but not least, we only looked at ligand geometries with large deviations, right? If geostandard restraints were fine, there's no need to try and get a different set of restraints. So we did this for these 1,700 ligands. So we refined them with the new set of restraints, and then we compared. And here I show you the mean portion angle RMSD averaged in resolution bins. So here on the x-axis are all the resolution bins ranging from 0.8 to 3.0. And here, again, in the same color code, the yellow curve shows you the torsion angle averaged in resolution bins for the geostandard restraints and in teal for the QMR restraints. And so across all these resolution ranges for geostandard, we have about 55 degrees of torsion angle RMSD, whereas for QMR, we have a reduction down to 15 degrees. So in all these cases, we get fewer deviations. So here are some practical aspects. This approach should be applied when the model is in an advanced stage. And the reason for that is that the binding pocket needs to be complete. So all the coordinating residues should be correct. If something is pointing into another direction, so we're not including a residue in the binding pocket, If it should be there, then this will obviously affect the QM minimization. And all explicitly water molecules should be explicitly modeled. So if there's some spherical blobs for water molecules, these should be placed as well, because they're also included into the environment cluster. The method is fully automatic, so I showed the things, steps one by one, but everything is done. The only thing the user needs to do is to choose the ligand that should be treated by this method, and it's available in Phenix as of now. So I don't think there is a standalone GUI, so you still have to use command line if you want to do that. Now, I said I was also interested if we can use this approach to validate ligands. Yeah, so can we glean any other information from this, what we're doing here in this minimization procedure of the binding pocket to validate if a ligand is there or not? So for example, if the QM minimization fails, or gives an unreasonable result, this could tell us, for example, that, well, the ligand doesn't want to be there. It could also mean that the binding pocket is simply incomplete or not quite right. So maybe that's one avenue. Then also what we can compare is how the ligand looks before and after. So we can calculate the RMSD before minimization and after minimization. And another thing is to look at energies, as we have seen in the talk before. That's also an avenue to for validation. So in the example that I want to show, I will focus here on the how the ligand moves after the minimization. So here's again one example. The diffraction data is 1.4 angstrom resolution, so quite high. And there are three ligands in this deposited model. One is BRL, that's a compound, I think it's called rosiglitazone. So again, it's a drug. And then we have two pegs of different lengths. So in this table here, for each of these three ligands, I have the real space correlation coefficient. I have the RMSD after this QMR minimization of these ligands in their binding pockets. And I also counted the number of clashes. So for all of these three ligands, we have quite high correlation coefficients, larger than 0.9. The QMR RMSD, so how much the ligand moves, varies though. So for this BRL molecule, it's only 0.5 angstrom square. And for the PEG molecules, it's more than 2 angstrom. And here we have the number of clashes. We have 13 clashes for the PGE compound. So let's look at these three one by one. So here is the
Sorry,
BRL.
Dorothee, you've got 2 minutes.
2 minutes?
Yeah, I've given him the 5 back already.
Oh, wow. Okay. Well, then let's go quickly through this. So here's the BRL molecule. Here, the density looks really clear, so I think there's no question that this is present or not. This is how it moves after minimization. Here's the PGE molecule. At the first glance, if we really look very quickly, it looks okay, but of course there's some issues we will look at later. This is how it is after minimization. And let's go back to the initial pose. Well, there are two issues here. One is there's a very short distance between this oxygen and the water molecule, 1.6 angstrom, way too close. That water molecule shouldn't be there. And then look at all these clashes involving the hydrogens. So there should be the oxygens in these positions closer to this lysine that is sticking up here. So a good idea is maybe to remove the water and refine. And finally, in this small PEG molecule has been squeezed into this electron density peak. After minimization, it is here. And well, there is not really an argument here that this PEG is really wrong, but still could be a good idea to remove it and refine. And maybe there could be a complete different scenario. Maybe it's not this particular PEG that's here, but a longer one whose ends are very floppy and we only see this one. But this is very difficult to figure out from here. But I think the take-home message is that these QMR RMSD can be very useful to flag some ligands that otherwise look quite okay. So to conclude, the QM approach is very helpful when you're dealing with flexible ligands, and sometimes it can be challenging to tweak the ligand geometry towards a conformation that fits into the binding environment, and QMR will do this automatically. So it's no need to know all the hidden options in all the restraint generator programs. And then the RMSD of the minimized ligand may provide a validation metric, but that also needs some more benchmarks. So more on QMR, this has been published, and this was a work with my colleagues Nigel Moriarty and Billy Poon. And finally, I'm working for the Phenix project, which is a collaboration between several different groups. With that, thank you for your attention, and if you have any questions.
One question for Dorothee in the interest of time, and you want to ask more, you can ask later.
Justin Bergman from the European Spallation Source. One quick question. When you have a charged ligand or metals with spin states, can you take that into account, or how do you treat them?
Yeah, I think we allowed charged ligands. About the spin states, I'm not so sure. I can, because all this minimization things have been done by Nigel. So if you want, I can put you in touch with him.
Thank you.
A very quick one. What is the PDB code for that last example?
I can share it with you. Yeah,
Okay.
on purpose, I don't like really sharing them in public, but I
Okay.
can tell.
Right. Thanks.
Mhm.
Okay, thank you again, Dorothee.